Good evening everyone. So welcome to my YouTube channel Math Sutra. So today we are going to see lecture first on convex function. So let's start today's session now. So what is convex function? Convex function. So let S be subset of R and S is non-empty. Okay. Then and S be convex. Okay, subset. So it means S be a non-empty convex subset of R. What is the meaning of convex subset? It means lambda x plus 1 minus lambda y belongs to S for all x y belongs to S. Okay, and lambda in between this range. Okay, then a function f s to R is said to be convex if f lambda times x plus 1 minus lambda y is less than lambda times fx plus 1 minus lambda fy for all xy belongs to S and lambda. Okay. So what is the meaning of this graphically? Okay, let's understand it. So this is x axis, this is y axis, and this is the origin. Suppose this is the function. Now you have one point x here. So this is my subset S. This is my S subset. So this is x here, and this is y here, and this is function fx. Now corresponding functional value is fx and corresponding functional value here. What is the linear combination? Suppose what is the lambda times fx plus 1 minus lambda times fy. So this will be in between here. And what is the linear combination? Convex combination, this 1 minus lambda y. So this will be somewhere. Okay. The corresponding image is here. Okay. Somewhere. So this is f times lambda x plus 1 minus lambda y. Okay. This is this. And what is this? This is So obviously this is less than this one. Okay, this is less than this one. So here f lambda x plus 1 minus lambda y is less than this value. So this is the meaning of convexity. Okay, we see some examples. First of all, observe one thing. Note that let S be a non-empty convex subset of R. Okay. Then F, okay, and F S to R be a function. Then F is convex. It means F is convex on S if and only if F lambda x plus 1 minus lambda okay, 1 minus lambda y less than equal to lambda fx plus 1 minus lambda fy. Okay. For all xy belongs to S, x not equal to y, and lambda in this range. Okay. So its proof is simple. If if f is convex on S, then obviously we have f lambda x plus 1 minus lambda y less than equal to lambda f plus 1 minus lambda y. For all x, if y belongs to S, x not equal to y, and in this range. Okay. Now conversely assume that conversely assume that f lambda x plus 1 minus lambda y less than lambda fx plus 1 minus lambda fy. For all xy belongs to S, x is not equal to y, and okay. Now let xy belongs to S. Then case 1, x is equal to y. Okay. If x is equal to y, then f lambda x plus 1 minus lambda y. Okay. For lambda, we have what we have, because f and those things are same. So I can write x in place of. So what is this? So this is lambda x plus x lambda x. Okay. So this is cancel out. This is fx. But this is equal to lambda times fx plus 1 minus lambda fx. Okay. It means, okay. So this is, I can write. So this implies f lambda x plus 1 minus lambda y is less than lambda fx. Now case 2 is that, what is case 2? Case 2 x is not equal to y. So for lambda in between 0 and we have already in assumption. So we take only lambda is equal to 0. Okay. Or lambda is equal to 1. Okay. For lambda is equal to 0, what is this? X. So we are take lambda is equal to 0, we are taking. So lambda x 1 minus lambda y. If lambda is 0, then this is 0 x and 1 minus lambda it will be y. So this is fy. So this can be written as 0 fx plus 1 minus 0 fy. So this is equal to lambda fx because lambda value is 0. So what we have f lambda x plus 1 minus y less than f. Okay. So this is done. So if lambda is equal to 1, then f x lambda lambda x plus 1 minus lambda y. So what is this? This is 1x. So this is 1 minus 1 y. So this is fx and this is 0 into y. This is fx. So this can be written as 1 into fx and 1 minus 1 fy. But lambda is 1. So lambda fx plus 1 minus lambda fy. So this implies f lambda x plus 1 lambda y less than. Okay. So this implies in this case we are done. Hence, okay, therefore f is convex on S, we can only. Okay, so this is done. This is so. So now examples of convex function. Examples of convex functions. Example 1, fx is equal to x is convex on R. Okay. Well, how? So let x, y belongs to R, x not equal to y, and I'm taking lambda in this. Then what is f lambda x plus 1 minus lambda y? Okay, so this is lambda fx, this is minus lambda fy. So this implies f lambda x plus 1 minus lambda y for all x, y belongs to R, x not equal to y, and 0 in this, lambda in this. What is the meaning of this? Meaning of this is, this implies fx is equal to x is convex on R. Okay. Example 2. Fx is equal to mod x is convex on R. Okay. So let x, y belongs to R, x not equal to y, and we are taking lambda in this range. Okay. Then f lambda x plus 1 minus lambda y, what is this? This is nothing but by definition. Okay. So how we can write it? We can write it like this. Okay. So this is equal to lambda x lambda y plus 1 minus lambda y. Okay. Because lambda and 1 minus lambda, because lambda is non-negative, so this implies, and this implies 1 minus lambda is equal to lambda. Okay. Lambda is less than 1. Because lambda in this range, so 1 minus lambda is also non-negative. So 1 minus lambda is also this one. So what is this? This is lambda x mod x plus 1 minus lambda mod y. So what is this? This is lambda x plus 1 minus lambda fy. So this implies that lambda x plus 1 minus lambda less than or equal to lambda fx plus 1 minus lambda. Okay. So what is the meaning of this? This is true for all x, y belongs to R, x not equal to y, and so what is the meaning of this? Is implies fx is equal to mod f is convex on R. Okay. Now third example. Example 3. Okay. Fx is equal to x square is convex on R. Okay. Solution. Let x, y belongs to R, x not equal to y, and lambda in this range. Okay. Then f lambda x plus 1 minus lambda y is equal to lambda x plus 1 minus lambda y का whole square, that is lambda square x square. Okay. and that is 1 minus lambda square y square, and that is 2 lambda 1 minus lambda xy. Okay. So this is equation number 1. Now, we know that 2xy is always less than x square plus y square. So from 1 and 2, we have so f lambda x plus 1 minus lambda y, that was f this square plus 1 minus lambda square y square plus lambda 1 minus lambda 2xy. In place of 2xy, we put x square y x square plus y square minus lambda square y square plus lambda 1 minus lambda x square plus y. To solve this x square, and this is 1 minus lambda square y square, and that is after solving it, what you will get? X square. Okay. Now combine with this one. You take this one and this one. Take this one. Okay. So what you will get? So what is after solving it? What you will get from here? So this is lambda square plus lambda square x square, and what is this? This is 1 plus lambda square minus 2 lambda, and this is lambda minus lambda square y square. So this is cancel out. This is cancel out. And what is this lambda x square? And this is 1 minus lambda y square. So what we got? We got f lambda x plus 1 minus lambda y, that is less than lambda. So what is this? This is nothing but lambda fx, and this is 1 minus lambda fy. So what we got? For all xy belongs to R, x not equal to y, and lambda integration. What is the meaning of this? This f is convex. Okay, remark. If f s to R is convex, then f restricted to s dash to R is also convex. Okay, where s dash is non-empty and it is subset of s. Okay, S. So its proof is simple. Let xy belongs to s dash. Okay, x is not equal to y and lambda in this range. Okay, since xy belongs to s dash and s dash is subset of s, this implies xy belongs to S. Okay. Now, xy belongs to S. X is not equal to y and lambda in this range, and F is convex on S. So this implies F lambda x plus 1 minus lambda y less than lambda fx plus 1 minus lambda fy. Okay. But this implies F lambda x plus 1 minus lambda y less than fx plus 1 minus lambda fy. But ultimately, where were the x and y? We selected x, y from S dash. So what we have? We have for all x, y belongs to S dash, x not equal to y, and so this implies F is convex on S dash. So this is true. Now remark, I'm writing again remark. Now take any interval, let I be any non-empty interval on R. Okay. Then fx is equal to x mod x and x square are convex functions on I. Okay. So it is simple because I subset of R, I is non-empty and I interval. Interval is always convex set. We know that interval on R is always convex. So this implies I is convex subset of R. Okay. Now x is equal to x mod x and x square are convex on R. We already proved. Now by previous remark, we have x is equal to x mod x and x square are also convex on I. Okay. So this is true. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much. We will see you for next lecture. Thank you very much.